When you have a headache, muscle pains, cramps, what pill do you reach for in your medicine cabinet? If you're like me, you reach for brand names such as Tylenol, Advil, Motrin, Aleve, or aspirin. But the next time you do, look on the side of the bottle and find the box labeled warnings. You'll see ominous language about liver damage, stomach bleeding, or taking the medicine while pregnant. Like all medication, these painkillers have desired effects and side effects. To understand why, you have to understand the biology responsible for the pain and how the medication treats it. Headaches, for example, can be caused by increased pressure from swelling around your brain. Headache medications fight pain by blocking a source of that swelling. This source is called an enzyme. Enzymes are like microscopic factories in your cells that convert one thing into something else. Think a paper factory. Wood enters on one side and paper comes out the other. The enzyme that headache medications block produces several different products from several different starting materials. Some products are involved in good effects, like protecting your stomach from its own acids or helping the development of babies still in the womb. Other products of the enzyme cause pain and swelling. Current headache medications block all the enzyme products from forming. This leads to the desired effect, your headache goes away, but also causes the side effects you see on the warning label. The question my research tried to answer was, can we make a new medication that only blocks the enzyme from making products that cause swelling? In other words, can we make a new drug that doesn't have a warning label? To answer that question, I first had to make a lot of new molecules. Fortunately, as a chemist, making new molecules is my specialty. I started with medications like Advil and Aleve and changed them in subtle ways. I added a few carbon and hydrogen atoms on one end of the drug or took away atoms elsewhere. Every time I made a new molecule, I did an experiment with it, the enzyme, and the enzyme starting materials. I measured how much of the good and bad enzyme products were produced. The molecules that did well on the test tube were then given to cells in a petri dish. Again, I measured what products the enzyme created. Finally, the two drugs that did well in the petri dish were given to mice. We recorded how long the drug lasted inside the mice as a way to estimate how long my new drugs would remain in humans. Unfortunately, none of the drugs I developed were actually good enough to test in humans. But my research could be useful to scientists in the future. I hope that one day, my research will contribute to a future painkiller that doesn't contain the scary phrase, "Side effects may include."